Today we will study the properties of colloidal solutions. In the previous lecture we have completed properties and preparation of colloidal solutions, and today we will study the properties of colloidal solutions. Is it visible? Okay, good evening. Okay, so properties. So first is physical properties. So colloidal solutions, what are their nature? Are they homogeneous or heterogeneous? Yes, tell me. Are they homogeneous or heterogeneous? So first is heterogeneous character. Those particles, means colloidal particles, they form heterogeneous solution. They always form heterogeneous solution because though colloidal particles, it seems like homogeneous to the naked eyes, but when we see it under ultra microscope, then we come to know that they are heterogeneous solutions. They are heterogeneous solutions. Yes, today it's I think visible. Okay, done. So they are heterogeneous, consisting of dispersed phase and dispersion medium, right? Now stability. So colloidal particles, are they stable or unstable? So keep in mind, colloidal solutions are quite stable and they settle down very slowly. Though say they do settle down, but very slowly. Okay, that's why they are quite stable. Now tell me about filterability. So if we use ordinary filter paper, then then colloidal particles along with true solution particles can pass through it. But if we use ultrafilter paper, or we use membrane, parchment paper or animal membrane, then colloidal particles cannot pass through it. So what I told? In ordinary filter paper, pore size is large, that's why colloidal particles as well as true solution particles both can pass through it. But in if we use animal membrane or parchment paper or even ultrafilter paper, that you know how do we prepare. Ultrafilter paper is prepared by using Glodion solution, 4% nitrocellulose solution in alcohol ether mixture. Okay, so in animal membrane or parchment paper, pore size is reduced, that's why colloidal particles cannot be passed through it. So that is the thing about filterability, means they can be removed by, they can pass through ordinary filter paper but cannot pass through animal membrane or parchment paper. Okay. Now visibility and color. So if we talk about visibility, so you know, colloidal particles are not visible to the naked eyes. Colloidal particles are not visible to the naked eyes because they are very small, but they can be seen through ultra microscope. We can see the particles through ultra microscope. Done? Means not visible to the naked eyes, but visible through ultra microscope. Right? Now color. So color, actually color of the colloidal particles, it depends on the size and nature of particles. For example, finest gold soul. Finest gold soul is red in color. It is red in color. But when particle size grows, then it turns purple, then blue, and finally golden color. Finally golden. So that means the size of the particle and nature of the particle decide the color of the colloidal particles. Now, if we have milk and water mixture, then it also depends upon the which light we are observing, reflected light or transmitted light. So see, if we look at the 90-degree, then reflected light and in transmitted light, colors are different. Transmitted light and colors are different. So if we look at the reflected light, this mixture looks like blue in color, and if we see the transmitted light, it is red in color. Transmitted light is red in color and reflected light is blue in color. So that means the color of the colloidal particles or solution first depends upon the size, second depends upon the nature of the particle, and third on the way in which we are seeing the light. If we see the reflected light, then color is different. If we see the transmitted light, it is different. Okay? And why it is so? Because of scattering of light by the colloidal particles. That we will discuss in the Tyndall effect in detail. Okay? Now, next is colligative properties. So in solution chapter we have done what are the colligative properties, that is relative lowering of vapor pressure, or elevation in boiling point, or depression in freezing point, or osmotic pressure. Right? So these properties are proportional to number of particles. It is independent, they are independent of the nature of the particles. They depends upon the number. And at the same time, first they are proportional to number of particles and they are inversely proportional to molar mass that we have done. Now you know, as colloidal particles, they are bigger in size than the true solution particles. That's why their molar mass should be more, and that's why their colligative property values are less. Their colligative properties values are less because these three represent a difference. Difference in vapor pressure, difference in boiling point, difference in freezing point. Only osmotic pressure is the one which has absolute value, and that is measurable even in case of colloidal solutions, and that's why it is used to determine the molar mass of the colloidal solutions, colloidal particles. Got it? Yes बेटा, ये पॉइंट समझ में आया? This one. Okay, done. Next is, this is colligative property. Now, next one is mechanical property. And main is Brownian movement. What is Brownian movement? It is zigzag motion of particles. Zigzag motion of particles like this. So actually this zigzag motion of particle is due to unbalanced forces by the dispersion medium particles on dispersed phase particles. That's why between two collisions it is a straight line, and when collision takes place, dispersed phase particle when collide with the dispersion medium particles, their collision are with different forces. Means dispersion medium particles collide dispersed phase particles with different forces, and that's why their direction changes every time when collision takes place, and that zigzag motion is called Brownian movement. You know, Brown on pollen grains, he did the experiment. He was botanist and he saw the zigzag motion of the particles, and that is the cause of Brownian movement. So colloidal particles do show the Brownian movement, right? So this is mechanical property, and cause that cause is that dispersion medium particles strike on or collide on dispersed phase particles with different forces, with a different magnitude of forces, right? Okay, next is optical properties. That is Tyndall effect. So when a strong converging lens is used, and that is passed through colloidal solution, this is colloidal solution, this converging lens, this is the lamp. Now when these forces, this light pass through it, there is a slit, and then light is passed through it. So when this light is passed through the colloidal solution, the path, when it is in the dark room, so that path of the light becomes visible. Now, and this is called Tyndall cone. This is called Tyndall cone because it was what is Tyndall effect? This is the scattering of light by the colloidal particles. Okay, scattering of light by the colloidal particles present in the colloidal soul, that is called Tyndall effect, and this part is called Tyndall cone. Now what are the conditions for Tyndall effect? First condition is size of the particle is not or is very much close to is comparable to wavelength of the light used. Means size of the particle and wavelength of the light, that has almost same value. They are not much different from each other. Okay. There is a large difference in refractive index of dispersed phase and dispersion medium. There is a large difference in refractive index of dispersed phase and dispersion medium. Only then Tyndall effect takes place, and this is the scattering of light by the colloidal particles present in the colloidal soul. This is only the Tyndall effect, and this is responsible for the ultra microscope, because in ultra microscope you are not able to see the particles, but you are able to see the bright stars. Like say, if this is the part, this is the colloidal solution, and we see it by naked eyes, we are not able to see the particles. But if we see it under ultra microscope, then we are able to see the bright stars. Means scintillation, that is the scattering of light by these particles, and by counting these bright stars we are able to calculate number of particles in the colloidal solution. So if we have this volume 1 liter and we counted the particles, then how many particles are present in 100 liter we can calculate. Just multiply it by 100. So number of particles in 100 liter we can calculate. So this is the principle of ultra microscope, Tyndall effect. Okay. This is the importance of Tyndall effect actually. Now electrical properties. So electrical properties means colloidal particles are charged actually, and all the dispersed phase particles have the same charge, and that is responsible for the stability of the colloidal soul. So electrical property is responsible for the stability of colloidal soul. Stability of the colloidal soul. How is it possible? That repulsion, actually when like charges are there, see, let us say these are the colloidal particles, and if there is a positive charge on the one, same positive charge is on the other. So you know like charges repel each other, and whenever there is a repulsion, what do we say? That it is unstable because of repulsion. But here this repulsion between the colloidal particles is a boon for the colloidal solution, for the preparation of colloidal solution, for the stability of the colloidal solution. Because colloidal solution is stable only because colloidal particles have the similar charge. How is it so? Because because of these like charges they repel each other, and because of that repulsion they remain at the safe distance from each other. They are not able to come closer. But when we add an electrolyte, this charge is neutralized, and therefore they collapse together. They coalesce means they coagulate, they precipitate, and that's why colloidal solution is unstable because of excess of electrolyte, right? So whenever we talk about stability, it is because of the charge on the colloidal particles. And if there is a positive charge on the colloidal particles, same magnitude of negative charge is on the dispersion medium. So overall colloidal solution is electrically neutral, but if we see them in separate, then dispersed phase particles have a charge, and opposite to that charge there is a charge on the dispersion medium particles. So if there is a positive charge on dispersed phase particles, if there is a positive charge on the one colloidal particle, dispersed phase particle, same charge is on the other. That means if positive charge is there, all the colloidal particles have positive charge, and dispersion medium has negative charge. So this positive charge is responsible for the stability of the soul. Now how do this charge develop? So first theory is due to rubbing of dispersed phase particles on the dispersion medium particles, okay, or electron capture by the air, like in Brady's arc method. We have done this. There is a negative charge on the metal because of that electron capture. But best theory or most acceptable theory is adsorption of the ions, that I told you in the peptidation, that colloidal particles, what they do, if we have silver iodide, then either Ag plus or I negative is adsorbed on these particles. Okay, so that adsorption theory is the best acceptable theory for charge on the colloidal particles. That we will do like this. See, we have two test tubes. In first test tube, we have AgNO3, A test tube, and we add Ki in it. In the second test tube, we have Ki and we add AgNO3 in it. So obviously when AgNO3 comes in contact with Ki, we get Agi as a sole particle along with KNO3. Right? Now tell me, in A, what is the charge on Agi? And in B, what is the charge on Agi? In test tube A, what is the charge on Agi? And what is the charge on Agi in B test tube? Yes, question for you. Fast. A positive charge. Very good, Anika. That's right. Actually, in this case, AgNO3 is in excess. It can be written as Ai in AgNO3. That means, in this case, AgNO3 is in excess. So, Agi adsorb either positive charge or Ag plus or I negative. So, as AgNO3 is in excess, so Ag plus ion is adsorbed on it. So, it is positive sole. Positive, and in this case it can be written as AgNO3 in Ki. That means Ki in excess. So Agi, there is a negative ion on it. So it is negative and this is positive. B negative. Very good, beta. That's great. Got it? Now, when this is formed, this positive ion attract negative ion towards it, and this negative ion attract positive ion towards it, because it is it is KNO3 is formed along with it, so K plus and NO3 negative. So that colloidal particle let us say this is the colloidal particle and it is positively charged. So this is the fixed layer. This one is the fixed layer. Now in the dispersion medium, if dispersed phase has positive charge, dispersion medium has negative charge. That means there is a negative charge on it. There is a negative charge and it is called mobile layer. One is fixed layer, other is mobile layer, and this is called Helmholtz electrical double layer. Helmholtz electrical double layer. This is Helmholtz electrical double layer. Okay. Now there is a separation of charges. Positive charge, fixed layer is positively charged, then mobile layer is negatively charged. If fixed layer is negatively charged, then mobile layer is positively charged. So in both cases, this double layer is formed and there is a separation of charges, and separation of charges is a seat of potential, and that potential is called zeta potential or electrokinetic potential. So if there is a question about zeta potential or electrokinetic potential, you will draw this picture that this is a colloidal particle. On this colloidal particle, one charge is adhere on it, adsorbed on it, that is, let us say, positive charge. Then dispersion medium is negatively charged and those ions are mobile. Okay, this is delocalized or mobile layer, and this fixed layer and mobile layer, that is called Helmholtz electrical double layer, and because of that there is a separation of charges, and that separation of charges leads to potential, and that potential is called zeta potential or electrokinetic potential. Done? Beta, any doubt in this part? Yes, beta. Zeta potential or electrokinetic potential. Can you write it? Yes, beta, you are right. It is. I said, is there any doubt in it? If you have any doubt, you may ask. Okay. Now, charge on the particles of common soul, like negatively charged particles and positively charged particles. Negatively charged particles and positively charged particles. Now all the metal souls like gold, silver, platinum, all are negatively charged souls. Got it? Metal or non-metal sulfides, like all sulfides like arsenic sulfide, okay, they are negatively charged souls. Positively charged souls, hydroxides like hydroxides of metal like ferric hydroxide, aluminium hydroxide, they are positively charged souls. Or hydrated oxides, hydrated oxides like Al2O3.XH2O, Fe2O3.XH2O, they are all positively charged souls. Even hemoglobin is also positively charged soul. Oxides of metal like TiO2, they are positively charged souls. Starch, gum, gelatin, they are negatively charged souls. Acid dyes, like Congo red, they are negatively charged. Basic dyes like Persian blue, okay, they are positively charged. Sorry, now these are positively charged and negatively charged souls. Got it? Okay. So that's it. That's all for today. Thank you so much. So we'll continue the class tomorrow. Okay. And I think tomorrow this chapter will be over. Right? Bye bye then.